Okay, so in this supplemental lecture, which is going to be quite short, we're just going to show how a conservative vector field conserves energy. So let's recall real quickly, we said a vector field is conservative if there is a potential function f so that the gradient of f is equal to our vector field. So now let's consider the case where f is a force moving an object along a path c given by, say, some parameterization r of t, where t goes between a and b. So we've seen that the work done, which we'll just denote as w, this is the line integral of f over this path, which, due to our parameterization, we can rewrite this as f of r of t dot r prime of t dt. Now what we're going to do is we're going to use a little physics. So recall Newton's second law. Well, in a first semester physics class, you'd write this as f is equal to mass times acceleration, but for us, we want to use vector notation. So we're going to have f of r of t equal to m a of t, which we can also write as m r double prime of t. So then if we put that back into our work formula, this says I have work is the integral from a to b of m r double prime of t dot r prime of t dt. Of course, I can move that m out front if I like, because it's a constant. And I have this equation. Now this isn't so helpful yet, but we want to notice a trick here. So if I take the derivative of the dot product of r prime of t with itself, well, remember that the dot product here, the derivative of it works just like product rule, only with dots. So we have this for product rule. And now, of course, it doesn't matter the order. So I can flip the order of this second one here. And it doesn't change anything because dot product is commutative. And so this is 2 r double prime of t dot r prime of t. And notice that looks an awful lot like what we're integrating except for the 2 there. So we can just divide both sides by 2 and we get r double prime of t dot r prime of t is 1/2 d dt of r prime of t dot r prime of t. But we know r prime of t dotted with itself is the magnitude of r prime of t squared. Which, in this case, we could, well, we'll just leave it like that for now. We'll come back simplifying this in a minute. So let's put this back into our formula for work now. So if work is equal to the integral from a to b, and we saw that that was an m, and then we had the r double prime of t dot r prime of t dt. And so we'll use this as, we can bring the m out front, and then we have the 1/2, and I have from a to b d dt of the magnitude of r prime of t squared dt. And now this is just the fundamental theorem of calculus from Calc 1. So I can write this as this is magnitude of r prime of b squared minus magnitude of r prime of a squared. And then notice this is really the magnitude of the velocity at b squared minus the velocity at A squared. And if we let v be our magnitude of our velocity vector, let's make it a function, so v of t is the magnitude of our velocity vector, then this becomes m v of b squared over 2 minus m v of a squared over 2. And if you've had elementary physics, this should look fairly familiar to you. This is just the change in kinetic energy. So let's write, let's let, say, capital B be the position, R of B, capital A be the position at R of A, and then we'll let K be M, let's say, make it a function again. Let's let K of B be M v of B squared over 2, so the kinetic energy at B, and K of A be M v A squared over 2. So this is the change in kinetic energy at A. So what we've calculated then is our work is K of B minus K of A, which is the change in kinetic energy. So that's one part of the equation. So those formulas, though you probably haven't seen them maybe in vector form, they're a little bit more familiar when we change them out of vectors. So we have 1/2 mv squared for our kinetic energy. That should be somewhat familiar. So now let's assume our vector field is conservative. We haven't used conservative at all yet. So let's say with potential function f. So we think we gave this above, we haven't used it yet. So then we define the potential energy at say xyz by p of xyz equals the negative of the potential function at that point. And now notice what we have. We can look at the work again, and this is still a to b of f dot dr. But now, since we're assuming our vector field is conservative, we can write it as this gradient. And now, of course, our fundamental theorem of line integrals gives that this is r f of r of b minus f of r of a. And so to match this with the potential, let's pull out a negative sign. Maybe let's write it like this. Negative f of r of b, so that's still positive, plus negative f of r of a. So notice you can go ahead and check that those negative signs match up with above, but the point is this is now the potential energy at r of b plus the potential energy at r of a, which I could also write as p of b plus p of a. So that relates our work to potential energy now. So finally, if we equate these two, above we had work was kb minus ka. So we have kb minus ka is the work, which is also minus pb plus pa. And so then just get all the b's and all the a's on the same side. So this gives me kb plus pb is equal to ka plus pa. So this is the energy at B, and this is the energy at A. So since we have a conservative vector field, the energy is conserved as we move from A to B. And that's why we refer to these vector fields as conservative vector fields.